Hey everyone, this lecture's on the pH scale. Let's get straight into it. Now, one fact that you will have to come to grips with is this one. When you look at the concentrations of hydrogen ions and hydroxide ions in water and you multiply them together, you always get a value of 10 to the negative 14. It's always the case, it's a fact. So let me illustrate this by example. So if the hydrogen ion concentration is 10 to the minus 4, then the hydroxide ion concentration must be 10 to the minus 10, because 10 to the minus 4 by 10 to the minus 10 is actually 10 to the negative 14. Let me give you another example. Actually, what I'll do is I'll just give you another example and show you that dot point. So another example would be if the hydrogen ion concentration is 10 to the negative 7, then the hydroxide ion concentration is 10 to the negative 7. In other words, they're then exactly equal, and that, if you recall, is the case when you're looking at pure distilled water. That is, the solution itself is absolutely neutral. So if you look at thinking about that subscript p, which means negative log to base 10, then this must be true. So if the pH equals 7, that means, of course, that the hydrogen ion concentration is 10 to the minus 7. The pOH, the negative log to base 10 of the hydroxide ion concentration, must also be 7. In other words, when you look at these p values, they're going to add up to 14. So, if the pH is 4, the pOH is 10. So, in other words, you don't actually have to talk about the pOH, you merely need to know what the pH is, and you can immediately know whether there's more acid than base or whether it's neutral. So when the pH is 7, the pOH is 7, in other words, the hydroxide ions and the hydrogen ions in effect cancel each other out and the thing's neutral. If the pH is 4, then the pOH is 10, but that's telling you that you've got 10 to the minus 4 hydrogen ions. You've only got 10 to the minus 10 hydroxide ions, so the pH must be, you've got more hydrogen ions than hydroxide ions, so it's acidic. So in other words, any pH value less than 7 means that it's acidic. And of course, conversely, any pH value greater than 7 is going to tell you that the solution is basic. Okay, so here we go. Here's some examples. Well, that's a no-brainer. It's pH 7, so the solution's neither basic nor acidic. It's neutral. pH is 8. That means that the number is above 7. Therefore, the solution is basic. And again, you can kind of think through this. The hydrogen ion concentration must be 10 to the minus 8, and the hydroxide ion concentration must be 10 to the minus 6. 10 to the minus 6 is a much bigger number than 10 to the minus 8, so it's more basic than acidic. pH 14, that's obviously very basic. pH 6.8, it's just below 7, doesn't matter, it is below 7 and therefore it's acidic. And pH 3.4, much more acidic than that previous example I just gave you. So what this means is there's actually a theoretical maximum for the pH scale, and that value of course is 14. So at pH 14, the concentration of hydrogen ions is only 1 by 10 to the minus 14. I guess you could imagine it could be even lower than that, but it really doesn't matter. I mean, that's pretty much 0 anyway. So in other words, pretty much everything is hydroxide ions. Now, the other thing is that there's a bit of contention sometimes in the textbooks about what the lower limit is. Some textbooks tell you it's 0, some textbooks tell you it's less than 0. let's just say that the lower limit is 0. I don't really want to get into the reasons why. And then for all practical purposes, the lower end of the scale is in fact 0. So the pH scale runs from 0 up to 14. Just for your note, if you're thinking, well, how can you have a pH of 0? Well, don't forget that that means negative log to base 10 of the hydrogen ion concentration. So if you take the anti-log of 0, what you'll find is the number is a 1, right? In other words, the log of 1 is 0. So therefore, at pH 0, the concentration of hydrogen ions is 1 molar. So how does that all look on a scale then? Well, here's one scale I've given you where we've got pH on this side. Here we've got our scale running from 0 to 14. There's neutrality there, where there's neither an excess of hydrogen ions nor hydroxide ions, and below that 7 value, of course, the solution's acidic, and above that number there, the solution is termed basic. What sort of compounds or solutions are we looking at here that have these different pHs? Well, if we start here at pH 0, which means the hydrogen ion concentration is 1, as I pointed out before, that means that if you look at something like hydrochloric acid, which is a very strong acid and gives up all of its protons quite readily, it would be a 1 molar solution. You'll notice here, this one's kind of interesting. This is very acidic, this solution, and yet it's a biological source. This is stomach juice, essentially, the stuff that's used to digest stuff. You can see here that it's very, very acidic. As we start approaching neutrality here, you can see urine sits in here between about pH 4 and 5. Blood's around about neutral pH. It's actually a little bit higher than that. I think from memory it's about 7.4 or something, but it's around about neutrality. Pancreatic juice there I won't mention. And the other one's sodium hydroxide, 1 molar solution. It's up there at pH 14. Here's another pH scale for you. I actually prefer the other one in a way because it gives you the molarity values, but this one's kind of interesting too. It's got some other stuff on it. This one's actually reading in the opposite direction. So there's neutrality there, and there's stuff that's more and more acid, and going down here it's more and more basic. You'll see here that milk is around about neutral pH, which is what I guess you'd expect. This is an interesting marker here. So fish, of course, are extremely sensitive to their environments, and it doesn't take that much of a drop in pH for them to be affected. And in fact, round about here, which I guess is just above vinegar, which is pretty nasty, I'd hate to exist in it, it will actually kill fish. You see we've got vinegar, lemon, and then battery acid is up here at around about pH 1, so it's quite nasty. Basic solutions, we've got baking soda, seawater, oddly enough, is a basic solution. Ammonia, you can buy that in the shops, it's very basic, and lye. Alright, that's the end of that particular mini lecture. There's a summary there of the lecture in total. I'm not going to go through that now and zip back here. Okay, that's it for acids and bases.